All right, so if you have two series that are convergent, then if you add them up, that will also end up being convergent. Is the converse of this true? No, one of the problems we did earlier proves this. Earlier we looked at and did that separation one where we ended up getting um, a limit that equal, or a sum that equaled 3/2. However, if you look at these individual ones that were being added up, this is the harmonic series, which we know is divergent. This is also divergent because it's very similar to the harmonic series. So if you have two divergent series, that doesn't necessarily mean that if you add them up that they are also divergent. But working off the one we did say, if you have two convergent series, then if you multiply by a constant or add or subtract those two series, they also are going to be convergent. Let's look at an example here of this one. So we want to find what is the sum of this series. So first off, one thing we can do is there is some constants in this one. So let's rewrite this. That first series, I'm going to write it as 3 times the series of 1 over n plus 1 plus, and then over here we got the series of, and I'm going to write this one a different way. We could write it as 1/2 to the n would be the same thing, because 1 to the n is always going to be 1, so we could write it as 1/2 to the n. All right, well, what do these two series, or what are these two series going to equal? This is one we actually did earlier. We'd have to do partial fractions and subtract, but looking back here at this one, we see that once we separated this and solved it, the answer did come out to be 1. That is a convergent series. So we know this one equals 1 for that result, but we still have this 3 that we want to bring with. So we did this one, see previous one. And then our other one over here, this is a geometric one, and we looked at geometric in a previous lesson too. Remember geometric, if you want to find that sum, we want to do our A1, our first term, over 1 minus our ratio for geometric. And so here we're going to have our first term, if we put 1 in there, would be 1/2 over 1 minus, and our R here is 1/2, and so this would be half as well. All right, so what's this going to equal? 3 plus, here we got, it'll end up being 1/2 over 1/2, which is 1, and so this is going to be an answer of 4, and so this one is convergent here to 4. So 4 would be the sum of this one. All right, so we've looked at what happens now if you add up a convergent series plus another convergent series. Your result is going to be convergent. What we're going to look at now is what happens if you add up a convergent and a divergent series. And what we're going to prove here is that that is going to diverge. So if this proof by contradiction works by, we're going to say the sum of these is converges. So if it converges, it's going to have a sum m. And we said A of n converges. We're going to say that sum is p. So if we multiplied it by a negative, that means the sum of opposite of A of n would be negative p. If we now add these two convergent series together, which we know if we add two convergent series, we should get a convergent series as well, that the sum of b of n would equal m minus p, which are both terms, meaning b of n should also be convergent. However, we said before that b of n is divergent, so you can't have a finite sum that's divergent, meaning that can't be true. So if you add together a convergent and a divergent, you are going to get a divergent. You can't get a divergent one to have a finite sum, so it's going to have to be divergent. So anytime you add two convergents, you'll get a convergent. If you add a convergent plus a divergent, we always know the sum is going to be divergent by the proof of contradiction right there. And then the last scenario, if we add two divergents, that's the trickiest one. In this case, we don't know. You're going to have to do more tests if you add two divergents, because it could be divergent, but as we saw earlier from here, that just because you're adding two divergents, you could also get a convergent answer. So the two divergent one is the trickiest one. That's one where we're going to learn some more tests as we go here that you can use to figure out whether that's going to be convergent or divergent. Let's look at this one. Is the sum of this series convergent, or is it going to be divergent? Well, let's take out those couple constants here. So let's rewrite this one as 3 times the sum of 1 over 5 to the n. And that now, taking that 3 out, we could also, because 1 to the n is the same thing, could think of this as 1/5 to the n. Plus, and this next one has a 2, so I'm going to pull the 2 out, and this would now just be 1 over n. So is this one going to be convergent or divergent? Well, looks like this first one here is geometric. It's a geometric sum. And this one should be convergent because remember we talked about if your R value, which in this case is 1/5, is less than 1, then it's convergent. So this should be a convergent one. We could find the sum out if we need to, but I don't think we're going to have to on this particular problem, because if we look at the next one, we see harmonic series. And we know harmonic series is divergent. We looked at that test earlier. So here, if we're adding a convergent and a divergent, we know that this sum is going to end up being divergent. And so we can say this whole thing here, this whole series should be divergent because we're adding a convergent one and a divergent.